By the way, I need to start saying that everything you're going to see that is smart or intelligent, it was all the work of Daniel. Any mistake that you see is probably my fault. So, I don't know if you know, but fresh water is not an abundant resource. Only 3% of total water resources are essentially fresh water, and 2/3 of that are in the ice caps, Antarctica and the Arctic. So it's only 1% that we're essentially used for consumption and also irrigation. And as you can see, particularly in California, but all over the US, probably all over the planet, droughts are a big issue and a big problem that affect crop yields and affect a lot of things. So specifically with respect to land coverage and turf, and that's not a very well-known crop. But if you actually go to the USDA, it's the largest crop in terms of surface in the United States, 128,000 square kilometers. It's actually 3 times the size of corn, which is the largest crop in the US. But we also use, lawns for aesthetics reasons. We like to walk on it, important people also in lawns. We love to interact, to sit on this, and we live in places that are, full of landscaping. You can argue it's cultural reasons and we may change the culture, but the reality is, that's what we have. And it takes a lot of water to irrigate all this area. In the order of 9 billion gallons per day. That's roughly 2 to 3 hours of Niagara Falls constantly just to irrigate our waters. Just to give you a perspective that this is a big problem. So, right now, we are doing a horrendous job at irrigating a very large surface area. And majority of the problems are, places are under-irrigated, which leads to really bad quality of service in terms of, the aesthetics of it, the plants suffer. And also over-irrigating, which is actually a more drastic problem. Leads to bad efficiency and use of the scarce resource, erodes the soil, and also it leaches fertilizer and chemical in the substrate of, different aquifers that are actually underneath. So we wanted to do a better job and try to solve that problem. So we took a look at the architecture of most irrigation systems at residential and even larger sources like stadium, universities, golf courses, etc. And most of these systems are actually controlled by a valve that activates the water and activates a line of sprinkler heads that are all irrigated. So the problem with this type of system is how you actually do control. Most of this is manually done. State-of-the-art industry systems use what I call ET, evapotranspiration system that are connected to a weather station, and then try to assume that you're going to provide enough amount of water of all the water that are lost due to weather. But the problem is that in most of these irrigation systems, the area that you're irrigating is not homogeneous. So what you really need is, for instance, in this case, because of over-elevation, because of different depth of the soil, because of different type of soil, because of multiple reasons, because of shadowing in a particular part of the area, you need to have enough granularity to irrigate differently. So in most of these systems, we end up with trade-off solution in which, because of one sprinkler or a group of sprinklers, you need to irrigate more. All the sprinklers in the line, because you have only one valve and actuation control, need to over-irrigate. So this is the problem. It's not like people are morons. It's just you don't have enough granularity of actuation. So over the past years, we have worked on this issue, and we have essentially gone into distributed actuation and centralized control. So we have replaced the single valve or multiple valves line by a valve per sprinkler head. And we're going to put intelligence in each sprinkler head, in which we're going to put a moat, we're going to put a solenoid, and we can choke the water or not. And we're also going to measure the soil moisture in the soil. So each sprinkler has a node with solenoid on-off control, a moisture sensor, and a radio. And they're going to transmit all these values into a centralized controller. A centralized controller, based on a model, is going to determine what is the solving and optimization problem. Is going to determine what is the optimal way in which I need to activate the sequence of sprinklers in order to minimize water consumption, but at the same time improve quality of service. And we have run multiple flavors of this, including Magic and the follow-up version of Vision that appeared recently, Dozen. And then we have also gone into, instead of first principle models based on partial differential equation, pure data-driven approach. Based on the information that we provide from the sensors, build data-driven models directly from the data. And we have been successful in doing that. In the last piece of work I presented last year, there was an issue that we actually put it in the paper, which was one of the centralized controller one day broke. Broke in the sense that it's not that it ran out of power, etc. There was a very, very critical problem in the serial communication between the mode that was attached to the Raspberry Pi that was acting as a controller that essentially prevent commands going out. And that led to an increase in water consumption one day, because obviously we want to continue doing research, and we put fail-safes in the devices that if you're in constant iteration for more than 2 hours, something is wrong, and we need to essentially cut off the flow of water no matter what. So the system actually recovered nicely. It over-irrigated one day, but then the next day you see it under-irrigated because it could measure and could react to that condition. It's like reacting to rain. But that was something that was in the back of my mind, that it's like the probability of this device was not that great. And we thought, okay, we can over-engineer the device, we can perhaps change the chips, the serial communicator, we can shield these things in order to perhaps deal with environmental conditions that we face. So the first thing that we thought is, okay, classic solution when you have a single point of failure, you just add redundancy. So we added more controllers. We ran the experiments in certain days, all of them failed. It's like, oh my God, we are in trouble here. So we keep adding more and more controllers, but they all keep failing. So we analyzed the problem, and it was essentially correlative failure due to environmental conditions. There were certain temperatures, certain humidity levels, certain days that led that all these devices were failing in cascade. So we thought, okay, classic solutions do not work. So we have to think about completely outside the box, so how do we actually make the whole system more reliable? There were other problems with centralized control. It's like the entire traffic has to go to a central place constantly, to provide enough information such that the central optimizer controller could provide information back. When we increase the scale of the system, that becomes an issue. The other issue, though, is that these model-based approaches, we're using all the information from the entire field. On a large field, that's a lot. So, computationally speaking, we were getting to the limit of solving this optimization problem no matter what type of model we were using, in terms of the scalability and the total number of sprinters we could use. So we decided to take a completely different approach in this. Instead of living with the limitation computationally, limitation in terms of reliability, a single point of failure, etc., we decided, okay, why don't we take a completely different approach, and instead of trying to maintain the state for the entire field, trying to have a single controller, we go fully into a completely distributed version. So the key insight here is, from the model perspective point of view, water irrigation that is in this little area at the back will probably not affect the grass cube. The water will not have a reach on the sprinkler head. Even the propagation, even if you have a slope area, the propagation at the surface and the propagation underneath the surface will not necessarily reach. So that is essentially a key insight in which you have a natural partition in the environment, and you can essentially partition the space. So instead of, we decided we're going to build local models that are only affected by local irrigation and my neighbors. And that means that I'm going to have each controller on each sprinkler head. And I'm going to only use local information that I measure myself and only from my directly connected neighbors. But that led to another problem. We decided, okay, what do we need to do in order to now move the centralized controller that is nicely written in an optimization language in Julia, with a nice operating system, with power resources, etc., to now use the battery operating modes that are in each sprinkler. And this is a nice idea. It solves all this problem, but you still have to deal with the issue of how do we actually do the optimization on the modes, which is kind of a complex task. The first thing that we faced was, okay, how do we partition them? And naturally, we kind of were lucky, the sprinkler heads, the radio of action was essentially limited. And it was essentially smaller than the radio communications that we were getting. So by simply detecting and doing running neighbor discovery, we could essentially determine what is my local field of action naturally. It was a natural way to partition the system. The other issue, though, is that we still need to go and do an optimization within each node. So just to give you an idea of what we're talking about, this is the natural view of the moisture level as a function of time for a 24-hour cycle. So we partition the irrigation and non-irrigation of a system in multiple settings. The first thing we should notice is this is a value that is called the PWP, which is called the permanent wilting point, which is the value of moisture that you need in order for the plant to avoid suffering. So this is something that determines the quality of service. That's something that you do not want to lower that. Otherwise, you're going to be affecting the health of the plant. So in general, at the beginning of the irrigation time, it should be very close to the minimum because you want to save water. And then you activate irrigation. And then once you stop irrigation, you reach a certain level. There's going to be a natural decay of water over the rest of the day, discharge, until you start the following irrigation cycle. So that's just normal process when you do irrigation. So you have the discharge, you have the daily minimum, and you can naturally partition the problem into a short-term model, which essentially leads to what is the movement of water and how the water will move in order to reach a particular state, and then the long-term movement. Once you reach there, just by the losses within the field and the movement of water, together with weather data and together with the minimum, you can essentially expect what will be. So, long-term model can be easily done with data-driven approach. You are gathering data over the entire scheme, so you can essentially feed any curve that you want. In general, we feed a simple detail with a simple regression based on past information. And the cool thing about this is that spatially you're doing in different parts of the field, which is that the curve is not going to be uniform and look the same. Different areas have different characteristics, but you can fit based on what you're using. Now, if you have the expected losses that are provided by the model, if you also know what's going to happen, what are going to be the losses due to evapotranspiration, that's something that you can get from weather data, that I'm not going to get into, and you also know the PWP in the field, you can essentially estimate what would be your goal state at the end of the irrigation cycle in order to find the minimum, the optimal minimum, such that when we restart the irrigation cycle, the whole process starts again. So the next step is how do you go and train a short-term model, which is while you're irrigating, how is the water movement model? And for that, we also use the data-driven approach. Essentially find the linear regression that essentially try to satisfy the following, which is given the current state of water moisture, this is all in vectorial form, and given the sequences of activation of the different sprinkler head within the space, what would be the expected water moisture at the next time step? And you do that particularly in our case, in our experiments, was essentially 1 minute. So you can get this information also from, directly from the data that you measure. At the beginning, we bootstrap the mechanism by activating the sprinkler head one at a time. So we have a seed for the model when we have no information about this. And as the day passes by, the model converges quite fast. So all this is to solve this problem. This is the optimization problem that you're about to solve. You're solving the minimization of the water use subject to a bunch of constraints. It sounds complicated, but it's not. So first, we have a physical solenoid constraint, which is we either activate water or not. We kind of, make it a continuous variable, even though it's a binary variable, because it simplifies solving the problem instead of in an ILP. It's a linear programming problem, so it simplifies the things. There are more details in here. I'll be glad to take it offline. That this assumption actually does not hurt the performance of the system. We also know that the water content should never be lower than the PWP at any point in time, because that's important, otherwise the plant health will suffer. And we also want to achieve a particular goal at the end of the irrigation cycle in order that if we go with the losses, we're never going to exceed the minimum. We know the initial conditions at the beginning of the irrigation cycle because that's something that the sensor provides to us. And finally, we have built a short-term irrigation model that essentially deals with while you're irrigating how the water is going to move in the short term. So given that, we want to go into completely distributed pipeline. We have now localized models that are only using this information from global neighbors. And we want to run the optimization. But if you see here, the size of my neighborhood is significantly smaller than the size of the total number of nodes that are in the system, which computationally help us to deal with this issue. Still, we have the issue of we need to run an optimizer doing all this and solving an NLP problem on a moment. And that was still challenging, but we thought this is the right way to do it. But we still have to solve this issue. So we tried to do it. We have run even machine learning, in previous experiments, in previous papers, we already knew about this initial. We have done logistic regression, we have done stochastic gradient descent. We thought we can do it. Too difficult. Too difficult, even to the point that the optimization metrics couldn't even fit in memory for the problem, even using the local memory. So we were going nowhere. Plus, porting all the libraries into TimeOS with no floating point, doing all these numerical tricks was too much work. So we took a look at how do we actually solve this problem, and we thought, okay, we can have Raspberry Pi Zero, which provides me a 1 gigahertz processor, has plenty of memory, run Linux, we can essentially directly port into this, it works fantastically with minimum effort, but it consumes a lot of energy, has no radio, very high power. So then came the idea, well, we need to combine the two features together. And that's what we did. We provided a co-processor hardware architecture in which the master is the one that is controlling the radio, is doing all the sensing, is doing all the communication between neighbors, and only when it needs to solve the optimization problem and the control problem, it activates the Raspberry Pi that is co-located, that is essentially provides the substantial data storage that you need and also performs all intensive computation in your application. Now, if you're introducing now a new high-power hungry device, our batteries are not very, very, very fast. So all issues with respect to system lifetime will suffer. So that was another problem we need to solve. It's like, okay, this works, computation works, is the right thing to do, we need to solve the energy issue. So how do you solve this issue? Well, we thought, this is another application. We could probably take advantage of some renewables. But then we tried solar, and it was impractical because people need to essentially cut the grass, mow the grass and the lawn. So what do you do? We cannot have things sticking out. We tried also temperature differential, based on depth, and trying to scavenge energy from there. It didn't work out. There was not enough delta T there, delta T in terms of delta temperature. But we thought, okay, we're morons. We have a lot of energy in the control that we're doing, which is the movement of water. That provides a lot of energy. So why don't we stick and we do energy harvesting with a micro-hydro water turbine? While we're irrigating, we're constantly scavenging energy that we can store to run all the electronics on it. So the contribution of this work are essentially the distributed control aspect, local modeling and optimization of the end devices at each fingerhead, the data communication only required to neighbors, and the new co-processor architecture to facilitate distributed computation. And we also introduce energy harvesting, that allows essentially perpetual motion of the data system. So that was a lot of work, mostly about Daniel. You see me here, there, trying to help him on some installation. So we needed to do a full test bed, doing the trenches, putting the PVC pipes, 300 psi, everything sealed, everything correctly installed. Otherwise, the university will come on there and will never allow me to do any sort of experimentation again on the field. And we deploy a test bed in an area in which we can test multiple different these systems side by side. And they're almost identical condition or as close as possible. So what we did is we tested our Wisdom system with the state-of-the-art industry standard, which is the evapotranspiration system, and also the PICS control system, which I was presented in previous year. That was essentially a centralized control. And these are some of the results. When we compare side by side, the first thing you notice is the ET system really, because it doesn't know the initial conditions at any part of the field, is trying to replenish the losses that you see based on weather. And it tried to do a relatively good job at that, but because it might be far off from the essentially minimum water requirements that are necessary, and because it's blind with respect to that, it just cannot do a better job. In Wisdom, the initial conditions that you see here were highly irritating in certain part of the field. So there were activation of the sprinklers daily, but there are some of the sprinklers that were not activated and that were decaying until you actually reach the minimum that is necessary. Otherwise, why waste water? So these are the initial conditions, and this is essentially probably a more accurate picture of what is the expected steady state performance of the system. So the overall numbers over the 2 weeks that we tested the system side by side are there. Kind of have an impressive 61% water savings, but that's a kind of a misleading number. In our paper, actually, we try to emphasize that the steady state result is probably the more important one. That is completely independent of the initial conditions. Then we compare this with the state-of-the-art academic work, which was PICS, with the centralized controller, also with the data-driven model. And you see here also the wildly oscillating initial conditions. It rained before the experiment, you had to wait a long time until everything turns out, but it's never perfect. So we start the experiment, and we got some results. And we also see a heavy, leaning towards wisdom in comparison to peaks. But again, this is a misleading number. You should expect the performance of both systems to be the same. The only thing that we're doing is we have a centralized solution versus a distributed one. But if you can see here, instead of taking the last days, they get into 4% of each other, which is the result that you expect. They're using almost the same. That makes both systems should be roughly the same. So we wanted to essentially also test what are the limits with respect to a local model, building an optimization model versus having a global model that should be optimal and reduce the quality of the solution in terms of irrigation. So we tried this by essentially, we didn't have enough large field to do it, so we had to go into simulation. And for that, we used the magic first principle model based on partial differential equations in order to essentially test the short-term irrigation model as a ground truth on the simulator, and then use a peaks long-term model between irrigation cycles. And we tested a different type of flat land, a sloped land, normal soil, clay soil, and also these very artificial 2.5 range sprinklers. Sprinklers in general have to have a distance between 50 and 75% of each other in terms of where the water reaches. But we purposely went to extremely wide ranges in which a single sprinkler would cover an area 2.5 times of the distribution of the other sprinkler on purpose. And we see that there was essentially almost no difference between the two, except for this very corner case at the end, where this is where the difference happens. So if you have an extremely bad setup system of sprinkler heads, where the range of the sprinkler head is actually much larger than the distribution of sprinkler heads that are in the system, which no landscape person would essentially deploy that way, then you start noticing the difference. So all in all, we try to provide all quality of service and efficiencies that we have seen in previous work with respect to peaks. We have distributed system that removes the limitation of the previous work in terms of single point of failure, computational limitations, and also decrease in all communication overhead. Energy harvesting allows perpetual system lifetime, and we have a flexible new hardware platform that enables in-network processing. So we started by wanting to have something like significant efficiency improvements, improved irrigation quality of the plants, automatic system configuration such that the person deploying the system doesn't have to train, doesn't have to program anything. The system will run itself all the conditions and adapt. Distributed operation that allows true scalability. Perpetual system lifetime, no battery changes, no one wants to deploy the system will continue running. And it's actually usable to control the real irrigation system. Thank you.